Okay, so looking at this first table, we see it's a decreasing table, going from a 17 down to a 14, down to an 11, down to an 8. So notice that it's going down right here, 3, and then it goes down 3 again, it goes down 3 again. So when we're just subtracting the same constant rate, we're going to say that this is a linear function because it is subtracting 3 each time to the previous term. You could say it has a constant rate of -3. You could say it has a constant first difference of -3, etc. And so for the recursive here, we'd say f of 3 equals 17. See where that comes from right here and right here. It's the first term in the table. And then we say that the recursive function to get the next term is the previous term -3 each time. And again, where does that -3 come from in the table? It's that constant first difference that we saw right there. Then we go to write our explicit. And our explicit uses those same 3 numbers in this order. We begin with 17, and then we're subtracting 3 x minus time 3. So remember that this 17 comes from right up there, the minusing 3 comes from right there, and the time 3 comes from the table right here. How'd you do? Okay, pause this video, go try the next table, let's see how you did. This one we see is going also decreasing from an 8 down to a 2. We see that goes down 6. Then it goes down 2, but then we see that it starts to go up 2 again. What kind of a function goes down and then back up? We're starting to think about that quadratic. So then from -6 up to a 2, we see that +4, and there's that +4 again. There's that first difference. Notice it's not constant, but then we see that second difference of 4 is constant. So we know we have a quadratic. Okay, so we go to write our explicit for the quadratic. We know that it starts with an x squared, and we're working with quadratics in the simple form of ax squared plus b. Sorry, ax squared plus c. So how do I get that a value in front right here? Remember that I've got a constant second difference of 4. So to get the a value, we take half of that constant second difference of 4. What's half of 4? There's where the 2 comes from. For our constant value at the end over here, I go look at my 0 term. Notice that in this case, this has a dot at the origin, 0, 0. So technically, could I write a +0? But do I even need it? I don't even need it. My explicit is just 2x squared. For my recursive, I see that it's an f of -2 equals 8. Comes from the top of your table there. And then f of x equals f of x minus 1. Here, for this linear change, this linear rate of change, we need to go do pick a row, any row, and see what do we see here is happening with each linear and first difference and second difference. So this is where we say begins with 2, adding 4, x minus 1, and we simplify. So I'm getting 4x minus 2 as your linear rate of change for the quadratic. I'm going to write that work over here somewhere, squeeze it in so it's in the same area. Let's use black. So it begins with 2 adding 4, x minus 1. Simplify. 2 minus 4. And there it is. All right, for the last table, do you notice it's just a nice little exponential one? How do I know it's exponential? Because it is half of the previous term. Okay, then for my recursive, we say f of 5 equals 40. F of x equals f of x minus 1 times 1/2. That's my multiplier. And then for my explicit, we say f of x equals, begins with 40 multiplying by 1/2 to the power of x minus 5. And you can have parentheses on these or not. You could also just put a dot to imply multiplication right there. So where do these numbers come from? Remember that this 5 shows up right there in the explicit. Notice that this 40 shows up right here in the explicit. And then this 1/2 shows up right there in the explicit. How'd you do?